So now let us do a practical on the convolutional neural networks. In this practical session, we will build a small convolutional neural networks having few layers, few convolution and pooling layers, and we will do this on a data set, an online available data set, that is MNIST, fashion MNIST data, that is available with the TensorFlow. Okay, the main library that is we are using is TensorFlow. Okay. In the introductory class, I told that TensorFlow is the environment, machine learning environment that is provided freely by. It is an initiative of Google. Okay, that Google Colab is also provided. Colab is also provided by Google. TensorFlow library has been developed, or the environment has been developed by Google, right? And all of these are freely available. Okay, and there are some predefined data sets are also there. Okay, so we can use their data set to train our model or to understand how CNN is working. Okay, so these are some libraries that we are going to use. Open the Google Colab and import these libraries. Now first we will build some model, then we will actually train our model with the data set. Okay, so now first understand what I have written here. So I have imported TensorFlow as TF. Okay, and inside the TensorFlow there is a lightweight library for machine learning and deep learning, that is Keras. And in Keras there is a function that is sequential. Right? So it will define or it will create a model. Okay, so that's why I have defined a model using the Keras sequential. Okay, because sequentially I am going to add the models. Sequentially I add the layers. Okay, so yeah. So can you tell me that whether the ANN practical has been done in Python or R? In which platform you have?
It is done in R, sir.
R. Okay. So for ANN also you can use this function. Okay. Right. So it will sequentially because in ANN also we are sequentially adding the layers. Okay. So you can see the definition here, that sequential function having layers and its corresponding name, right? Like this you can add. So this is a definition of this. Okay. Now we will add a layer here. Okay, so if I comment all this and I run this one, only this one. Okay, now I will see the summary. I think it will give me error because no layer has been added yet. Okay, because it is currently it is empty. Now I will add a layer. So while adding the layer, let us understand what the layer is. Right. I am adding a convolution layer here, convolution operation. Okay. As you can see, the 2D convolution layer, this layer creates a convolution kernel that is convolved with the layer input layer and produce a tensor, means produce a feature map. Because in the higher dimensional means the matrices are known as tensor. Okay, that's why the name TensorFlow has been coined. Okay, so what are the components here? So the first component, it is I am as let me show the, yeah. So the definition is, the first it is saying filters, that is the number of filters. Okay, or the kernels, right? The weight matrices. So the number of weight matrices we have to tell the layer, okay, while adding it. Then there is a kernel size, that is 3 by 3, 5 by 5, 7 by 7, whatever, okay. Then stride I already told that when we are shifting our that kernel from one position to another in the image. So if it is 1, then it is shifting 1 position. If it is 2, it's 2 by 2, then it is shifting 2 position, like that. Then padding is that padding with zeros in all the 4 sides, okay. Then data format is that whether we are having the data in that whenever we are mentioning or we are applying the images, we have to mention the format, whether the channel is in the last in the last of the that vectors matrices, or it is in the first, right? So that is the thing. But in case you don't have to mention this one, okay, it is not mandatory. By default it is none, right? Because every time our channel is in last, that is the that RGB channels, that is 3, we are mentioning it is in the last position, okay. If it is in first, you have to mention it as channel first, okay. Then these are not important. Then activation function we have to define, okay. That is, we are using ReLU. That use bias, you already know that there is one bias term there, and it is by default it is true, so no, we are not mentioning it. Then kernel initializer, like as someone was asking that what is the value of the kernels, but the values we don't define, but the distribution of that kernel, okay. Yeah, sorry, not this one. So the distribution of that kernel is defined by this kernel initializer variable, okay, like this. So there are any other variables or parameters are there, but those are not of concern. Right. So let us see what values we have defined here. So I have written that 32 kernels or 32 filters will be there, okay. Then the kernel size, I have chosen a kernel size of 3 by 3, right? Then a stride of 1 by 1. That means we are shifting the kernels one position at a time. Then padding, padding. Here the valid means there is no padding. Okay, and padding same means there is, you are adding one zero to each side of the image. Okay, then activation is ReLU activation function. Okay, here you can define any other activation function also. Then we have to define the input shape, right? I will tell this or I will discuss this later. What is this shape here? Okay, so let us run this one. Okay, then check. Yeah, now see that the sequential model has one layer having convolution. Now we will add a max pooling layer. Okay, generally we use max pooling, okay, because it has the ability to reduce the size, okay, and it also means holds the in small translations, right? Okay. So what it is, or what is the definition of this? Okay, it downsamples the input along the spatial dimensions, and it is having that parameters like pool size means the kernel size, but the kernels having no value. Okay, again we have to there is stride option is there. By default it is none. You can give padding is also there. You can add padding. Okay, and like that. Okay, so because it is a small size image, so we have taken pool size of 1 by 1. You can take it as 2 by 2 also. Let us take as 2 by 2. Now let us run this. So max pooling has been added, right? मैंने यहाँ पे 2 by 2 pooling size लिया, so its size has been reduced, right? अगर मैं इसको 1 by 1 करूँगा तो size will be, and one wonderful thing you can see that there is no parameters to learn, okay, because यहाँ पे जो kernel और pooling size जो हम use करें that having no parameters or no values in that. Okay, so let us say we don't want to. See, so हमने kernel को 1 by 1 किया, मतलब each individual को हम check कर रहे हैं, right? You can do that, or you can also do or you can add padding. Then you can apply the size of that 2 by 2 also. Okay. So let me give this one also. Right. Now, as we have discussed that the pooling generates a 2D matrix pool feature, we have to flatten that. So there is a flatten function here. So there is no parameter in this one. So it will just convert this 2D matrix to a 1D vector. Okay. So let us change it as 2 by 2 because 1 by 1 means it is giving the same output here. So after flattening, we will apply a dense layer. This dense layer is the nodes of the means the traditional artificial neural network. If you want to define artificial neural network using the TensorFlow, you will use dense. Okay, dense means just densely connected neural network. That is the activation artificial neural network. So it is having units. You have to mention the units. That is the nodes. Then there is activation function, and there are some. So if this is in case of the artificial neural networks, so these things you have to mention, but in case of the CNN, you don't have to mention this one. Okay, so here I have mentioned units of 128. So these values are user dependent. You can choose any value. These are all there is no fixed rule that you have to mention 128 or 256. Okay, you can choose of your own, but it is a good practice that you should put a number that is represented with the power of 2. Okay. Right. So suppose if I run this one, I will, yeah. So the flattening के बाद मेरे पास एक vector आया, that vector having this number of neurons, this number of nodes. Okay, or means जो 1D vector हमें जो मिला feature map से, right? क्योंकि 13 by 13 का feature map थे, there were 32 feature maps, pooled feature map. Okay, so in तीनों का multiply करेंगे, so we will get this one. Okay, and again after that we have added a dense layer, that is the first input node for the classifier network. Okay, right. So अभी तक हमारा classification करने का जो full model hai, that is not developed yet, but we have added one convolution, one pooling, then flattened the pooled layer, then we have added a dense layer. Now after that you have to add the last layer, that is the main classification layer. Again it is defined by the dense layer. In that case you have to mention the number of classes in your data. Right. So in the in our whatever the data I am using here, fashion MNIST, that is having 10 classes, so I have mentioned 10, and in this layer you have to mention the activation as a softmax activation function. So ultimately when the inputs are mapped to the 10 output nodes, so the values of that output nodes are converted to probability distribution, right? The probability values of the corresponding classes. So suppose I have this and check this. See, so 10 layer has been 10 layer added, and finally the output will be shown. Okay, so we got a model, we developed a model, right? Complete model CNN, and we want to train it with a data set. So now let us see the data set. Okay. अच्छा, मैंने ये कोड नहीं दिया ना आपको.
Sir, like this we can add any number of polling and
Yeah,
conditions.
any.
We have added only one.
Yeah.
But the flattened dense, those layers will be only one.
Flatten will be only one. Okay.
Dense also will be.
So this will be the interconnection between the last the convolution or pooling and the dense layer. Okay. Before this one you can have n number of convolution max pooling, and after that you can have n number of dense layer. Okay, and the last layer will be the dense layer with the units having equal number of units according to the number of classes in your data set. Okay, so this is the simplest one convolution, one max pooling, one dense layer, and finally the output layer. So इसी network पे हम एक model run एक data train करते हैं. So let us see how the model works. ठीक है, तो fashion MNIST data, it is available with the TensorFlow. Okay, it is having it is a grayscale image. Okay, there are 70,000 images in 10 categories, and the image size is 28 by 28 pixels. Okay, क्योंकि small size images ही करेंगे, क्योंकि larger size images होगा तो training में time लगेगा. Okay, and we have to use GPUs for that. Okay. So for importing the data set from the TensorFlow, so the data repository in the TensorFlow is having inside the Keras, there is a data set variable or the data set function, and on that there is fashion MNIST data. ठीक है, तो इसको हम we will extract the data. Okay. There is a load data function. So what the load data does, it means it is already defined that the MNIST data is divided into two sets, training set and testing set. Okay, and their labels also. So in this case, 60,000, that means I think 60,000 images are in the training data set and 10,000 in the testing data set. So let us import the dataset into training and testing variables. Okay, now let us see the shape of the dataset we have get here. Okay, so the training dataset having like 60,000 images, and its size is 28 by 28. Okay, testing having 10,000. Now we will store the names of the classes in a list, okay, or in an array by using this. Okay. So if you see yes, these are the class names. Then I have printed the images, that how the images are shown. Okay, you can do this or it is not required. At least you can see this. This is how the image actually looks. Okay. Now so each classes में क्या-क्या images हैं, few images we can see here. Let us see 10 images only. Okay, तो 10 images को उनके binary form में यहाँ पे we can print here. So ankle boot is this, like this one. Okay, हमने 10 by 10 का size लिया है. Okay, so you can see this one. These are not mandatory part. These are only for the validation of the images, that you are considering the right images or not, or whether you have actually read the images or not. Okay. Okay. Now we have to reshape the training and testing images. Okay. As we saw here, the shape is first is giving the number of images or the length of the data set. Then second and third are giving the size of the image, that is height and width. Okay. But in case of CNN always read an image in three dimensions. That is, first is height, then second width, and last is the channel. Okay, the channel is 1 whenever we are considering a binary image or a grayscale image, right? Or if we are considering a RGB image, then it will become 3. Right? So, but the MNIST fashion MNIST data is a grayscale image, so it is 1. But by default, it is not coming in the shape, so we have to reshape it. Okay, so reshape it means the first in the shape variable, the first parameter will be the length of the images, right? How many number of images? So we are getting this from the shape function, or the first position of the shape function. Then we are we know the size of the image, the height and width both are same, and we are adding another parameter, the fourth parameter here, that is 1. Okay. So, let me and the images that we have read are in NumPy array. So we are mentioning that you should consider it is a float values. Okay, that means real numbers, okay, or decimal numbers. So let me run it. Okay, and now you can see the shape. No. So you can see the shape, the one has been added in this shape variable here. Okay, so in previous, when we check the shape, it is having only three variables. That is, it is giving the length of the data set, the height and width. Now it is giving us the depth of the channel of the images. Okay, we have extracted the labels also. Labels mean the classes, class values. Here, training and testing, right? So, but here the training and testing were simply lists. Okay, but we have to reshape them, or we have to convert them into a categorical way. Okay, in this format, right? So there are 10 classes, and we have the labels, list of labels. So we will convert them into a categorical value. Right? So these are converted into categorical. Now there is one thing is that you can pre-process the image. Okay, as I already told that the grayscale images having 256 levels, that is the pixel values are from 0 to 255. So you can scale them to 0 to 1 by dividing them with 255, or you can skip this one also. Okay, so let us do this. Okay, so our data preparation, or we have read the data, and we are ready to train our model, because we already deployed or already built our model, defined our model. Okay, now we have already built the model with one convolution, one max pooling, then one dense layer having 128 units, and finally the dense layer having the actual number of classes. Okay. Right. Now there is one thing that we have to do is we have to compile. Okay, compile the model. Okay, so there is a compile function. Okay, the compile function having mainly three important parameters. One is optimizer. Right, optimizer means the optimization function. Right? The optimization function that that optimizes the network by updating the weights. Okay, so most commonly the Adam optimizer is used. We all are using Adam optimizer. This Adam optimizer is the most widely used optimization function. Okay. Then there is a loss function, means loss variable. For the multi-class classification, we use categorical cross entropy loss function, right? And there are many other functions are also there. Sparse categorical cross entropy are also there. But for binary classification, we use binary cross entropy, right? Or for that case also you can use categorical cross entropy, but in case of multi-class you can't use the binary cross entropy. And we have to mention a metric here. Okay, by default we have to mention the accuracy, because we will check, or the most important metric here will be the accuracy, the training accuracy of the model. Okay, so we have to compile this. Oh, sorry. Yeah. Okay. Now we have to train the model. Okay. For training any deep learning or the CNN or the ANN, we have to use a fit function. Okay. So let us see what the definition of the fit function here. Just a second. Yeah. So there are some parameters here. Yeah. You can see the fit function having parameters of x, then y, then you have to mention a batch size, then epochs. Verbose is not required. Callbacks. The callback is required if you applying some other things like you have mentioning your own learning rate, right? Or you are applying some other technique to save the model. Okay. Then there is one validation split. So if you don't have your training testing data in separate, you can mention here the validation split. Okay. And if you are mentioning validation split, then you don't have to mention validation data. But if you are not mentioning validation split, that means you have separate training and testing data. You mention the testing data here, the validation data, or you can keep it none also. Right? And these are some other things. Okay, those are not that much of concern. Okay. So the main things are, this is the X, the training images, and Y is the training levels. And we have to mention the epoch. Okay. And obviously we have to mention a batch size. Suppose I am taking batch size of 4. That means it will take 4 images at a time while training the model. Okay. And the validation data is testing images and testing level. Okay. So now we are ready to train our model with 5 epochs, right? So let us do this. It will take few minutes. The training has been completed. Means the 5 epochs we have completed, and we got training accuracy of 94% and the validation or the testing accuracy of 90%. So it is quite good. Right? Let us see the graphs here. So when the model fits, it is generally storing four variables. That's the training accuracy, validation accuracy, training loss, and validation loss. And based on that, we can have the insight of how the model is being trained with the dataset, or what is the trend of their training or training accuracy or validation accuracy, or the losses, how the losses are changed. Okay. Now let us plot the training and validation accuracy. So here, as we can see that the training accuracy is increasing, having an increasing trend. But the red one is the validation or testing accuracy. at first it was increasing, but at some point it is getting decreased. Right? It may be because we have less number of epochs here. Right? And we can saw the or see the loss here, the training loss having a decreasing trend, right, monotonically decreasing, but the testing loss at first it was decreasing, but after a point it getting increased, right? But so this is not a good model, right? From the accuracy point of view, we can say it is a good model, but it is not a good model, because the loss is validation loss or testing loss is getting increased while the training loss is decreasing. So it having some overfitting problem, that it is performing well in the training data, but it is not performing well in the testing data, right? And for checking the what is the effect of the model in the new data set, because whenever we are using the here we are mentioning the validation data as the testing images and testing labels, but in case of improving the performance of this model, this data has no effect. It is just showing us that our model is in this epoch, it having training accuracy of 86%, but in the unknown data set, it is having accuracy of this much, right? So this will tell us that whether our model is getting overfitted or not. But in case of learning the features, this data set has no role while the training process is happening. Okay. So don't get confused that I have used this data in the training phase, and again I am evaluating or telling that the model's performance is 90% in the same image. Okay, so this is already new to the model, right? Model hasn't seen this data while training the images. Now there are two functions there to have insight of the model's performance. That one is confusion matrix and another is the classification report. So these two functions are available with a different library, that is scikit-learn. Okay. In scikit-learn, there is a function that is metrics, okay, and on that package we are having classification report and confusion matrix. Okay, so confusion matrix, as you already know, that confusion matrix give us the what are the means give us the insight of the performance of the model, that how it is related to the original data set, that is what is the true positives, what is the true negatives, okay, in a tabular format. So in case of multiple classification, you can have this type of confusion matrix. So let us see. Okay. So the diagonal elements are representing the true positives for the this data set. Okay, and the classification report, it gives us the detailed report about the precision recall and F1 score, and this precision recall and F1 scores we can also have the, those variables from the confusion matrix, right? But you have to calculate it manually. But classification report give us the these reports easily in a tabular format. Okay, so class wise, it will give you the precision recall and F1 score. Okay, so here in each class there are 1,000 images, and these are the overall report. So let us do another example or another model, define another model, like having two more convolution layers. Okay. So let us suppose there is a convolution of 64 kernels, and again a pooling. We are applying pooling here, and we are pooling size is mentioning 1 by 1, so that the size will be maintained here. Right? And again, there is another convolution layer with 64 kernels, and after that we are applying max pooling with 2 by 2 pool size. Okay, now let us see. Let us run this model and check the summary of that model. See, the convolution, this one having input, and there is max pooling. Then the second convolution, right? That's how the parameters are changing. So there are now around 1,88,000 parameters here. Now compile this one. Did I give this? Okay. Now let us change it to 2 because it is taking a lot of time here. I think 32. Okay. Now let us train it. Okay. Okay. Again, it increased a little bit. So let us see the graph. So see. Okay. So, but the accuracy is increased a little bit, right? It is now 92%. Okay. And the validation loss decreasing trend hai, that is not big, it is small. So if अगर आप लोग epochs अगर increase करेंगे तो maybe you can see some good results here. Okay. So this is all for this lecture.